Now let us move on to example number 7, the first example in this section for the optimization problem. So please pay full attention. A rectangle has a constant perimeter P. Find the length and the width. If it has a maximum area, hence find the maximum area. So here we have a few questions to be answered. So in order to do that, let us have a diagram of a rectangle in the first place, where the width of the rectangle is labeled as x and the length of the rectangle is labeled as y. And again here, the area of the rectangle, as mentioned in the question, is denoted as capital A and the perimeter of rectangle as P. So the step 1 is to identify the variable to be maximized or minimized. So since in this question we have two things, one is area and the other measurement is perimeter, we need to be clear on what need to be maximized or minimized. So as the question mentioned, maximum area and find the maximum area, it is very clear that the variable to be maximized is the area of the rectangle. So for that, we will write the area of the rectangle, which is A, is length times width. So A is equals to x times y. This variable A is now consisting of two unknowns, which is x and y. Now we are in step 2, in which we need to make the formula to be maximized in this question as a single variable function. As we know, we are dealing with area in this question, which was written as x times y. Obviously, this function involves two different variables. We need to convert this into a single variable function. For that, we need to write either a in terms of x or y alone. For that, we need another formula or relationship which involves x and y. In this question, we were given perimeter, where the perimeter of the rectangle can be written as 2x plus 2y. From this formula of perimeter, we can make either x or y as subject. So choosing y to be the subject in this case, 2y can be written as p minus 2x. Calculating further, y can be written as p minus 2x divided by 2, in which we can have y as 1 over 2 p minus x. Now, this expression of y in terms of x can be substituted back into the formula of area. Therefore, area can be written as x times y as 1 over 2p minus x. Expanding this function, we will have half of px minus x squared. In step 3, we will solve for f prime of x equals to 0. So as we have written a in terms of x completely, we are able to differentiate this function of a with respect to x, where half of px, remember p is the constant parameter, therefore differentiating half of px will be half of p minus 2x. And equating this, dA over dx equals to 0 will gives us 1 over 2p minus 2x equivalent to 0. Here again, remember, variable is x. So solving for x will be 2x equals to 1 over 2p. And simplify further, x will be 1 over 4p. In this step 4, we will verify the first derivative function by using second derivative test. We start with dA over dx, which is equivalent to 1 over 2p minus 2x. This is our first derivative for the function in this question. For this function, we will find the second derivative, which is d2a over dx squared, where the answer is negative 2, a number which is less than 0. When we observe that the second derivative test is a negative value, the x critical number we obtained for this question, 1 over 4p, will give us a maximum result for this question, which is area to be maximum. In step 5, we are in the final stage of finding the optimization value, which is the optimum area, the maximum area. So for that, we start with x equals to 1 over 4p as we known earlier, and this one going to give us the y value which is corresponding to the x. So for that case, y must be calculated using 1 over 2p minus x function, in which we can substitute x to be 1 over 4p. So the y is here as 1 over 4p. For this pair of x equals to 1 over 4p and y equals to 1 over 4p, we can calculate the maximum area as x times y, where 1 over 4p multiplied by 1 over 4p will be equivalent to 1 over 16p squared. So this is the solution.